Now we want to consider section 9.4 and also go back and pick up some things from section 6.5, which is exponential growth and decay. So I wanted to treat it in this chapter rather than the inverse chapter because this is where we actually solve the differential equation that governs exponential growth. So with exponential growth, we've got lots of natural phenomenon that have rates of growth that are proportional to the amount that's there. So these would be things like animal populations, bacterial growth, radioactive decay or radioactive dating, drug elimination from the body, and continuous interest, and actually also Newton's law of cooling. It begins to be exponential. So the things that govern exponential growth, or the equation that governs exponential growth, is what's called the law of natural growth. So the law of natural growth says if you're considering a constant y that changes, a function y that changes with time, and dy dt is a constant times y, so that's saying the rate of change is proportional to the amount that's there, where y is a function of time, then we have a differential equation there that's separable. We can multiply both sides by dt and divide both sides by y. So multiply by dt and divide by y on both sides. And what we have left then is dy over y on the left and k dt on the right. So now our variables are separated. We can integrate both sides. And this integral on the left-hand side, that's natural log. Right-hand side is k times t. Don't forget your absolute values. So ln absolute value y is kt plus your constant. And then we want to undo this log to solve for y, so we exponentiate on both sides. E and ln cancel each other. You get absolute value of y. And then e to the kt plus c on the right-hand side. And then we want to break this up again. Multiplication, when you multiply exponentials, you add the exponents. So we want to do that backwards. So if we do that, we get y, which is plus or minus e to the kt plus c. So first thing I did was get rid of the absolute values. And then next, we added the exponents that comes from this multiplication, e to the c times e to the kt. Well, this constant here, plus or minus e to the c, we're going to rename that and call it a for amount. So that gives us y equals a e to the kt. And then notice that a is not equal to 0 because e to the c is always positive and the plus or minus would be positive or negative. But notice here that if you go back to our original differential equation, if y is equal to 0, if a equals 0, that gives y equals 0. If y is equal to 0, dy dt is 0, but then also k times y is 0. So we actually don't need this restriction that a is not equal to 0. Notice now that if you plug in 0 for time into your equation here, you get a times e to the k times 0. E to the k times 0 is 1, so that's just a. So that initial, the initial amount, or the initial amount of whatever you're talking about, that's your constant out in front. So the solution for the law of natural growth is y of t is y of 0 e to the kt. Okay, so everything that's exponential growth, this is the equation. All right, well, let's put it to work. So what happens if we consider a bacterial culture that initially has 500 and grows to 1200 in 3 hours? We want to find the following. First, y of t. And we start with y of 0 is e to the kt. And then what do we know here? Well, initially there are 500. That's y at time 0. And then 3 hours later, we've got 1200. That's y at time 3. So we are given that y of 0 is 500 and y of 3 is 1200. So the y of 0 equals 500, that's just the constant out here in front. So that lets us update that equation to 500 e to the kt. And then your second condition, that's going to give your constant. So we're going to plug 3 in for t right here. So y of 3 then is going to be 500 e to the k times 3, t is 3, and set that equal to 1200. So now we can solve for k. So let's divide the 500 off both sides. And then notice we've got a common factor of 100 on the right hand side that we can cancel out. These guys cancel. So we get now e to the 3k is 12/5. And then we want to undo that exponential. So we will take a log on both sides. ln and e cancel. So we're left with 3 times k is natural log of 12/5. And divide both sides by 3. K is 1/3 times the natural log of 12/5, which to 6 decimal places is 0.291823. Okay, so now what we can do is take that and plug it back in here for k. So that gives us the equation y of t then is 500 e to the 0.291823 t. And again, use several decimal places with that constant. So we've got our y of t. Okay, what else? Well, what if we wanted to know what's the doubling time? So how long does it take to double? Well, it goes from 500 to 1200 in 3 hours, so it's certainly less than 3 hours. Well, how do we find it? Well, take your y of t here and set it equal to double the 500. Set it equal to 1000. So take your y of t, which is 500 e to the 0.291823 t, and set that guy equal to 1000. Okay, well, this is just an exponential equation. Why don't you pause the video for a second and solve that and see if you can find the time. So we're going to divide both sides by 500, right? And on the right-hand side, we just get 2. On the left-hand side, 500s cancel. We get the exponential all by itself. Undo exponentials with logs. So natural log on the left and natural log on the right. These guys cancel each other out. So we get 0.291823t is log of 2. Divide off that constant in front. So t is log 2 over the 0.291823. And that gives 2.375 hours to 3 decimal places. And what else can we find? Well, what would be the time to reach 10,000? Okay, we know how to get to 1,000 double. What about 10,000? Well, we would take our y of t, which is your 500 e to the 0.291823 t, and set that guy equal to 10,000, and then solve that equation. And we've done lots of these, so it's the same steps as in part B here. We're going to divide both sides by 500. That gives us e to the 0.291823 t is 20. We are going to take logs on both sides. ln and e cancel. Gives us 0.291823 t is log of 20. Divide off your constant out in front. So t is log 20 over 0.291823. And that is approximately 10.27 hours. So this has grown pretty fast. And this is why infections can be a problem in the body, because they multiply so fast.